Okay, so in this video we want to look at piecewise functions. In an earlier study design, these were referred to as hybrid functions, but piecewise functions is more consistent with how other regions of the country and the world talk about these kind of functions. Essentially, a piecewise function, formerly known as and perhaps referred to by some teachers as a hybrid function, is a function that's defined by different rules over different subsets of the domain. So your function might have a domain of R, but perhaps from negative infinity to 0 it follows this particular rule, and from 0 to 10 it follows this particular rule, and from 10 to infinity it follows this particular rule, whatever it might be. So here we have an example of a piecewise function. So it can have two or more branches to the function. This function has three different branches, so three different rules over three different subsets of its entire domain. So the function follows the rule 4 minus x squared, where x is between negative 3 and 1 inclusive. It follows the rule x minus 1, so a linear graph where x is between 1 and 5 not inclusive, and it follows the rule negative 5, so that is y equals negative 5, so a horizontal line at negative 5 when x is less than negative 3. And so we get this picture here. So it is really just, if you're sketching a graph of this nature, it is really just sketching three different graphs in one. Okay, so you're looking at the graph of, 4 minus x squared, which is a parabola translated up by 4, x-intercepts at plus or minus 2, but you only want to look at that graph from negative 3 to 1 inclusive. So when x equals 1, that's at that point there, 1, 3, subbing 1 into the rule, we can work out 4 minus 1 squared is 3, and negative 3, when x equals negative 3, 4 minus negative 3 all squared is 4 minus 9, so it's negative 5. So negative 3, negative 5 would be that point there. So we're only looking at this bit of the graph. Okay, so that's that top line. And then we'd be looking at the graph of y equals x minus 1, which is a not a horizontal line, which is a straight line with a gradient of 1 and a y-intercept at negative 1. We can work out that the x-intercept is also positive 1, so we're looking at this particular line here, but we're only looking at that where x is between 1 and 5, not inclusive. So when x equals 1, when x equals 1, we can sub it in y equals 0, so that's the point 1, 0. When x equals 5, 5 minus 1, so that's 5, 4. Okay, and we're only interested in the graph between those 2 points. Hollow circles at either end to indicate that those points are not included. And then finally, we're looking at the line y equals negative 5, so a horizontal line at negative 5. So let's get rid of that bit as well. Horizontal line along y equals negative 5 when x is less than negative 3. So there's our horizontal line. We're only interested in that when x is less than negative 3. Obviously that's going to be the point negative 3, negative 5. So it's going to meet at that same point there. Now there's a number of things to talk about here. In order for a piecewise function to still be a function, it's important at these sort of crossover points between the different functions that you don't have both points included. So for example here, when x equals 1, we've got when x equals 1, the parabola is defined, but the line is not defined. So there is still only one point. So this graph passes the vertical line test when x equals 1, i.e. it's still a function, because it actually only hits the graph here. Okay, it's not actually hitting the graph here. That's a not included point. So that's really important. Other things that can happen at those sort of crossover points would be what we're seeing happen here, which is the graphs actually meet. And it's really important to understand this. So although x equals negative 3 is not included on the blue line, it is included on the green line, and they're the same point. Okay, so some students I find get themselves in a real mess, and they try to, at this corner here, draw an included and a not included point. Something can't be both included and not included. The point is either included or it's not, okay? Is the point 3, negative 5 included somewhere in this function? Yes, technically it's included on this green branch, but it doesn't matter. It's included on the function. The graph's going to be continuous at that point. We're just going to draw it. There's just going to not be anything happening here. It's just like saying, the graph is continuous at this point. There's no hole there. We don't draw anything special there. We don't draw a big solid circle there. The graph just keeps going right on through it. So if the graph keeps going right on through it, that's all that's going to happen here as well. Okay, so it's just a nice, not smooth join, but it's just a nice place where the curves join. Endpoint here is not included. Again, like any other function, all endpoints should be clearly either included or not included. They should be marked with coordinates, so I've added all of those on here. And axis intercepts marked as well. Okay, they're already included, but we can add those on with coordinates if we want. -2, 0. This one's also an endpoint. So making sure all those key features are labelled. I think I've probably talked through all of these things. So it's the graph of the parabola over that domain, the line over that domain, and the horizontal line over that domain. Note that the piecewise function has two endpoints where there is a discontinuity at x equals 1. Okay, so that's what we were talking about here. When x equals 1, we get what we call a discontinuity. We'll talk more about that down the track. Okay, so the graph is discontinuous here. We get this jump in the graph. And so it's really important that we're clear about which endpoints are included and which ones aren't. So either they both won't be included, in which case that's a hole in the domain, or one should be included and the other not included. They can't both be included or it's not a function. Two different graphs meet where x equals -3. So I'm reading down here. Since both graphs have the same y value at this point, two graphs that meet where x equals -3, since both graphs have the same y value at this point. Because the graphs join, we would say that the piecewise function is continuous at this point. As I said, we can draw it without lifting our pen. It just continues through that point. There are no endpoints here, and so closed/open circles are not relevant at all. It's not an endpoint. The graph continues smoothly through that point. Not smoothly, but it's joined at that point. So let's think about the domain of this entire function. So it continues off forever down here. It doesn't continue off forever up here. Okay, so domain is going to continue down this way and it's going to stop here. Now, there's not a hole in the domain here because when x equals 3, that point is included on the green graph, and there's also not a hole in the domain here because when x equals, that should say -3, there's also not a hole in the graph. The graph exists at that point. So the domain is going to be just -∞ up to the x-coordinate of that purple point at the end there, 5, not inclusive. Now the range, and we see the graph doesn't go any lower than -5, and -5 is included. And we go up here, and it doesn't go past 4. Now, 4 is not included in this point, but it is included here at the turning point. So there is an included point on the function somewhere which has a y-coordinate of 4. So our range is going to go from -5 inclusive up to 4 inclusive. Okay. So again, I know there's a hole here, but there's a point where y equals 0 over on this part of the graph. Okay, so y equals 0 is still part of the range. And so that's going to be our domain and our range for that piecewise function. Okay, let's have a look at, this is the same function, so it's helpful to think back to this graph in helping to answer some of these questions. So we have the same function that we just examined previously, and we want to find h of 2, so we want to find certain things to do with this function. So h of 2 means replacing the input of the function with 2. Now, we don't replace all the x's with 2's and make a big mess of everything, because h of 2 means when x equals 2, what does h of x equal? Now, x equals 2 is only going to fit into one of these 3 branches, okay? So x equals 2 fits somewhere in there, okay? And so therefore, h of 2 goes into that branch there, okay? 2 minus 1, and so it's 1. If you look graphically, you're looking at when x equals 2, what does the function equal? So when x equals 2, that's here, the function equals, it's the purple linear graph that we need to look at. We're not interested in the parabola because the parabola is not actually drawn when x equals 2, okay? Alright, h of -6. So -6 is in this part of the domain. And so therefore, this is the rule that we're interested in. So no matter what x is, h is always equal to -5, so h of -6 will be -5. h of 0, okay, so in which section of the domain is 0? So that fits in that section, so we're going to substitute it into that bit of the rule. 4 minus 0 squared, so 4. h of 8, now 8's outside of the domain, so h is not defined when x equals 8. h of 8 is undefined. Again, we can see on the graph, 8's out here. There's nothing happening here. There is no graph out here. Okay. h of 0, as we just worked out, goes to, is part of the green part of the function. h of negative 6, when x equals negative 6, is part of the blue part of the function. So that's those previous two examples we've just looked at. Okay, h of 2a. Okay, now we don't know what a is, and so therefore we can't work out which specific branch it goes into. And so therefore, in this instance, h of 2a, we do have to put it in everywhere. Here and here, but also here and here. It's going to adjust what's happening with our domains. Okay, so our function becomes 4 minus 2a all squared, where, negative 3 is less than or equal to 2a, which is less than or equal to 1. And then it becomes 2a minus 1, where 2a is between 1 and 5, not inclusive. And then, it's not 2x, 2a. And then negative 5 when 2a is less than negative 3. Okay, so what we've done here is create a whole new function that's in terms of a, not in terms of x. So let's just simplify things here. So we've got, that's going to be 4 minus 4a squared. And if we simplify this inequality to make a the subject, or to make it all about a, so dividing everything by 2, that rule only applies between negative 3 on 2, where a is between negative 3 on 2 and 1 on 2. We have the rule 2a minus 1, where a is between 1/2 and 5 on 2. And we have the rule negative 5, where a is less than negative 3 on 2. Okay. Essentially, this is taking the entire original function and dilating it by half from the y-axis. We'll talk more about transformations in a couple of videos' time. Part F of the question asks us to find the set of values of x such that h of x is equal to 2. So now we could go blindly straight into the function here, and we'll talk about what happens if we do that, but we have got a graph up here. So what we want to think about is we're looking at when h is equal to 2, so that's the line y equals 2 intersecting with y equals h of x, and there are 2 points where that happens. One on the green part, so the quadratic part, 4 minus x squared, and one on the purple part, the line, so 1 minus x minus 1. So we're going to need to solve those two things. 4 minus x squared equals 2, and x minus 1 equals 2. Okay. Now we do need to be a bit careful and make sure that any solutions we get fit the domain for that particular function. So for example, if we set this bit equal to 2, the solutions have to be within this domain. Okay, so if we look at 4 minus x squared equals 2, that's going to be x squared equals 2, so I've added x squared and taken away 2, and so x is plus or minus root 2. But for this branch, we know that x is between, what was the domain for this branch? Negative 3 to 1 inclusive. Now root 2 is about 1.4, so positive root 2 is not within this domain, so that means x equals root 2 is a solution. If we look at the second branch of the function, the rule is x minus 1, setting that equal to 2, we get x equals 3, and we need that to be in the domain, we need that to be in the domain 1 to 5, which it is. Okay. Alright, so you have to make sure that it's within the required domain, so that one's okay. And then we could think about the third branch, which is just negative 5 equals 2, which is obviously not possible at all, so we're not even going to think about that. We were asked for a set of values of x, so let's say therefore x is an element of the set root 2, 3. Alright, let's have a look at one more example. Let's sketch the graph of another piecewise function. So we've got f of x, it is the graph of 2x plus 1, where x is between negative 3 and 1, not including negative 3, but including 1. it is the graph of 3 on x, so a hyperbola, where x is bigger than 1, and it is the graph of 2, sorry, the spacing's not that great in that setup, where x is less than -3. Okay, so we probably want to sort of do some planning, kind of think out a bit what this looks like. That's a straight line, so let's work out the endpoints of that, because they're going to be the highest and lowest values. 2x plus 1, when x is -3, that's going to be -6 plus 1, so -5. And then when x is 1, that's going to be 3. So that line is going to sort of go from, you know, -3, -5 up to 1, 3. So just to sort of think through the scale of things. Then we've got the hyperbola. So when x equals 1, y equals 3, so it's actually going to join on to that graph there. And then as x gets bigger, it's getting smaller and smaller, approaching the, you know, x-axis, sorry. And then x equals 2, sorry, y equals 2 when x is less than -3. So we're going to sort of have something like that. Alright, so in terms of y value span, we need to span from -5 up to +3. So I'm just sort of thinking that all through a bit before I draw a formal graph. Oh, sorry. Alright, 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3. Okay. So what did I say? For the linear graph, when x equals -3, y equals -5, and that's a not included point. So -3, -5, up to, now it's going to have an x-intercept at -12 if you solve that equal to 0. So it's going to go, going to hit through there. It's going to put a y-intercept at 1, so it's going to hit there. And when x equals 1, y is equal to 3, and that's an included point. Okay, but we already worked out it actually meets with the hyperbola at that point. When x equals 2, we have 1.5, or 3 on 2. When x equals 3, 3 on 3 is 1. Okay, it's a hyperbola, so it's getting closer and closer to the x-axis as we head out that way. We've got our straight line. Use a ruler if you're not too good at drawing straight lines. So that's the point 1, 3. This is 0, 1. This is -1/2, 0. So all intercepts still being marked, plus any, you know, joining points or endpoints. We've got this last bit here, y is equal to 2 when x is less than -3. So when x is less than apologies, slight interruption to recording there. I've lost track of where I was at. So we're just drawing in this last part of the graph. So y equals 2 when x is less than -3. So not including this point at -3, 2. Horizontal line before that though. Okay. So we see here actually neither of these points is included. So that's fine. It's still a function. It's not breaking those rules of a function. But we want to think about that when we think about its domain. Okay. Alright, so let's have a think about what we've got here. So the domain of f. So this function has a name. So dom f for the domain of f. Goes right down, it's heading off down here to -infinity, it's heading on up here to +infinity, but there is this x value here at x equals -3, which is not included in the domain. Okay, so the domain is all the real numbers except for -3. And then the range of f, so in terms of y values, lowest y values down here at -3, but that's not included. All the way up here to +3, that is included, okay, and it exists everywhere in between there. So obviously we've got a bit of a hole here, but there are still other points where there are y values of 2. Okay, so our range goes from -5 not including -5, up to 3 including 3. Try that again. Okay, so sketch the graph, state its domain and range. So we've got all axis intercepts labelled, all sort of, we call this kind of point here where two curves join at different slopes, a cusp. Okay, so that's a cusp point. It's an important key feature of the graph where the functions join, or also important where the functions don't join. So making sure that those are labelled with coordinates. Okay, piecewise functions with your CAS. If you want to sketch a piecewise function or define a piecewise function, your CAS actually used to work a lot more nicely with piecewise function. We often use piecewise functions when we're looking at continuous probability distributions later on in the course, and it did used to be really helpful to be able to define a piecewise function. But I find that some changes in operating systems since then, the CAS doesn't quite handle algebra with it as well as it could do. Anyway, let's have a quick look at, let's define this one we've just done. So menu 1, to define a function, I'm going to define f of x, it's going to be equal to, so I've just hit that template palette, the button up next to number 9, and then we've got two options for piecewise functions. This would be just one with 2 branches. This one will allow us to choose how many parts to the piecewise function there are. So create a piecewise function with 3 function pieces. And then I just simply enter my function in. So 2x plus 1, where negative 3 is less than x, which is less than or equal to 1. And then 3 on x, where x is bigger than 1. And then 2, where x is less than negative 3. Okay, so there's our piecewise function. So if, for example, we wanted to work out what is f of 0, it will work out which branch is relevant to that, where do I put it. So obviously it would go in this top function here, 2x plus 1, and when x equals 0 we get y equals 1, which matches with what we're seeing with the graph here. Okay, we could have a look at, f of 1 is going to be equal to 3, f of 10, it's going to be 3/10, that's going to be way up here, so quite a small value. F of negative 3, for example, is undefined, and that's because neither of those points are included. We could solve our function, our piecewise function, equal to a value. So let's say when it's equal to 1, so there should be 2 points where that happens, at the y-axis there and somewhere else on the hyperbola here, at x equals 0 and x equals 3. Okay. Oh, sorry, didn't mean to delete the y-axis, just try and delete that. Let's see what happens if we solve it equal to 2. There should be one solution here, but then there should be infinitely many solutions down here. I'm not sure what it's going to tell us. Let's try it. Solve it equal to 2. There you go. F of x is equal to 2 when x is anything from negative infinity up to negative 3, not including negative 3, or when x equals a half, or when x equals 3 on 2. Great. You could also get your CAS to graph it. So if I've already defined it over here, pressing my scratch pad button to flick across to the graphing screen, f of x, don't need to retype it, I've already defined it, and my CAS can sketch it for me here. Obviously I can explore that using graph trace or analyze graph, but personally much easier to find all those key points over in the calculator screen. Alright, so that is the theory on piecewise functions.